everybody, welcome back to my YouTube channel. In this video, we will discuss what self-attention is, and believe me, this is by far the most detailed and simplified video on YouTube where we will be explaining everything in a very detailed and intuitive manner. We have enough analogies and examples to give you. So, subscribe to my channel and let's start this video. Okay, so before jumping into what self-attention is, let's just answer a very basic question, and that is in order to perform any natural language related task, for example, let's say I'm doing machine translation. So, whatever we provide as input in our model, in which form is it present? So, it is quite obvious that our models are machines, they don't understand natural language, the language that we speak, right? What they understand are numbers. So that is why whenever we perform any kind of natural language processing tasks, for example, sentiment analysis or machine translation, the inputs that we provide here are actually the numerical representation of that word. We can't directly pass word as input here because our machine will not understand. The language that they speak is the language of numbers, and the language which we speak is something that they don't understand. So that is why we don't directly pass the words inside our model and we pass numerical representation of our word. That is what our input is. Now the question is that how do I convert my word into this numerical representation? So to convert our word in numerical representation, we have various techniques in NLP. For example, one hot encoding, where we represent every number in a vector form where elements are either 0 or 1, right? Similarly, we have BAGO words, we have TF, IDF, but these techniques just convert the word into numerical representation. That does not carry any meaning. So that is why another techniques were introduced, for example, word to vec. Now these types of embeddings carries the semantic meaning of the word, and similar words will have similar representations. So they will have similar numbers in their vectors. And it works on that ideology that if words are used in similar context, then those words must be similar. So if I am saying that I play cricket in cricket ground and I say I play hockey in hockey field, then by word to word technique, the embeddings that I will get for cricket and hockey, they will be very close because they are used in similar context. So this is what word to vec technique is. It not only represents the word in numerical representation, but it also captures the semantic meaning of the word. Similar words will be present in the similar space in the vector field. They will be in the similar space, right? They will be in the similar, they will be they will be very similar to each other. Okay. And the embeddings that we get from here, those embeddings are called word embeddings. These are nothing but numerical representation of the word that carries the semantic meaning of the word as well. For example, if I have to represent apple, then I may represent it this way. Okay, so this is my word embedding. Or let's say I am representing Samsung, then it will have a very similar representation with it. Okay. And these numbers can represent various aspects. For example, this might represent technological company, right? I'm just giving a random guess here. Not exactly this, not exactly what I'm saying. It might not represent that exactly, but each number carries certain aspect of it. That is why they land up in the similar area, right? Now, everything seems good, right? But there's one big problem with word embeddings, and that is that they are good in capturing the meaning of the word, but let's say I have a sentence like I like apple juice, and let's say I have another sentence that I use apple phone. Now, apple here is the same word, but it is used in different context. Right here, apple represents the apple juice, the fruit, and here apple represents the company that manufactures phone. Right? So this word is used in different context here, but when word embeddings are generated, these embeddings or these numerical representations are actually static. By static, I mean that once they are generated, they will remain same irrespective of how apple is used in the sentence. So it's like a blurred average of meanings, blurred average of meanings. So let's say I have a very big data where 90% of the time I am referring apple as a fruit, but 10% of the time I am referring apple as a phone. Then the word embedding of apple that will be generated using this data will will capture more its fruit component, right? So let's say if I have a vector where this represents the fruit component of it, then let's say that is 0 0.9, and let's say if this represents the technological component of it, then let's say 0 0.1. Now this same word embedding will be used everywhere. Now let's say during testing phase I came across a sentence where apple is used as a technological organization. So do you really think that this embedding will be right fit to use there? No, right? So these word embeddings are static, and that is what the problem is. It would have been better if we can generate dynamic embeddings based on the context of the sentence. For example, if apple is used as a fruit here, then it should have a different word embedding. If apple is used as a company here, then it should have a different word embedding or the numerical representation. So that is where self attention comes into the picture. Self attention is a technique. For now, you can consider it like a black box. We will be uncovering the details of this box, but for now, let's just consider here that it's a box that takes in the word embedding of a word or a token more specifically, and in return, it gives you contextual embeddings. Now, what these contextual embeddings are, what we discussed so far. So these are dynamic representation of the word, dynamic representation of the word, numerical representation of the word that depends on the context. Okay, that depends on the context. So from vector embeddings, we jumped to word embeddings. These vector embeddings were not able to capture the semantic meaning, so we moved to something that was able to capture the meaning of the word. And with the meaning of the word, there was one problem that it was static. It was a blurred average of meanings. We wanted something more specific that changes based on the context that is there in the sentence. So that is why from word embeddings we moved to contextual embeddings. So whenever we want to convert our word embeddings into contextual embeddings, we use self-attention. Now there are more details into it, and we will see how we end up later. But for now, you can think of it like this way that in input, we are getting word embeddings, and the output that we are getting after all the processing that is happening here, the output that we are getting is contextual embeddings. Now let's see how we can generate these contextual embeddings. So a very basic idea is that let's say we have two sentences. The first one is use Apple phone, and let's say the second one is drink apple juice. drink apple juice. So up till now, in our word embeddings, what was the case? That for this apple and for every apple that appears in the sentence, the embeddings used to be the same. And what we want is that depending on the context, depending on the sentence, we want a different embedding for the word, right? And how we can achieve that? Let's start with a very simple basic idea, and that is, what if we represent every word on the basis of the words that are present in the sentences? So if I have to represent apple, then that would be how we have the word use, then apple, then phone, and we are adding them up all, right? Similarly, if I am saying that what is the embedding of apple, then what I am doing, that I am taking up all the sentence, all the words in the sentences. Juice. Okay. So clearly you see that this is already solving our problem, because earlier this apple and this apple, they have the same vector representation. But now what we are saying, that apple's numerical representation will be the word embedding of use plus the word embedding of apple plus the word embedding of phone. Similarly, for the second sentence, if I am finding out the word embedding of apple, then that would be word embedding of drink plus word embedding of apple plus word embedding of juice. So you see here what we are doing, that now we have clearly separated these embeddings. They are clearly different. Why they are different? Because in two sentences the words are different, and because the words are different, their embeddings are different, and when we are adding them up all, then the sum that we are getting is also different. But there is one problem here. Do you really think that in order to find out the vector representation of apple, every word has equal importance in obtaining it? No, right? We can't have same weights for every word. Some words have a very strong influence on our word. For example, when I am finding out the embedding of apple, then juice, drink, they are playing some part in obtaining it. But juice plays a very important role in finding out the correct embedding for it. Same way here, use, apple, phone, each one of these word embeddings will play some role in finding out the contextual embedding of this apple, because every word is part of the context. So that is why every word will play some role in finding out what the new contextual embedding of the word is. But some words will play a more important role. For example, in this sentence, since this apple is used in terms of in terms of a company, then this phone will play a very important role in obtaining this, right? So we need to associate certain weights here. We need to associate certain weights here. And how will we introduce the weights? What will be the value of weights? So a very simple idea is to find out the dot product between the word whose contextual embedding we want to generate. So we are taking its word embedding and we are finding out its dot product with the word embedding of that another word. Okay, so this is what we are saying, that we take the word embedding of our word whose contextual embedding we are finding out, and we are taking a dot product with the word that we are currently looking at. So why we are finding out dot product? Because dot product tells us that how much alike these two vectors are, or how much similar these two vectors are, how much related these two vectors are. So if the value of dot product is high, that means apple and use, they are very much aligned, they are very much related. In finding out the embedding of apple, use word embedding will play a very important role because they're very much alike, they're very much related. So this is what dot product tells us, and that is how we find out the weights. So now if I have to find out the new embedding of apple, so that will be dot product of old embedding of apple with use, and we are taking the embedding of use itself. Similarly, we are taking the embedding of apple and we are finding out its dot product with apple. Then we have embedding of apple. If I just go down here, we will have, let me erase this thing. It will be embedding of apple with dot product with embedding of phone and embedding of phone. And we are getting the new embedding of apple. So what we are saying that in contextual embedding, the embedding of the word should depend on the context that is there in the sentence, and the context depends on the words that are there in the sentence. So that is why the new embedding is depending on every word, but we can't assign equal importance to every word. That is why we have associated certain weights with it. And how are we calculating the weights? The simplest way is to find out their dot product. That will tell you how much related those two vectors are. If their dot product is high, that means their weight value, because dot product is nothing but your weight value, right? So if your dot product is high, your weight value will be high. That will mean that the importance of use word is more in finding out the apple embedding. That would mean that apple is more related to use. So that is how the entire setup is. Now, there's one more step that we do, and that is because this dot product is not scaled, it can have any value. We want it to come between a certain scale. Basically, we want to normalize it so that every weight we have adds up to 1. Okay, so that is why we pass these weights through SoftMax layer. And in return, what we get? We get numbers or the weights whose sum will be equal to 1. Okay, and they will range from 0 to 1. Their sum will be equal to 1. So we pass these weights through the SoftMax layer. Now, whatever we have discussed so far, can you point out the problems that we see? The problem is that these embeddings that we are getting, they are good. They are general contextual embeddings. But what if I have a task specific contextual embedding? Wouldn't that be better? We will understand what task specific contextual embeddings are, but it would have been better that instead of general contextual embeddings, if our contextual embeddings were task related, that would have been better, right? If somehow the information that is present in our data, our embeddings can learn from them. It can inherit the patterns from the data. That would have been better, right? This is first thing. And second thing is, currently we are not at all taking into consideration the sequence of the words. For example, if I write cat, chased, mouse, or if I write mouse, chased, cat, then in each of these sentences, the cat will have the same contextual embeddings. Why? Because the words are same. But don't you think that embedding should be different here? Because the context is different, the meaning is different. Here, the cat is chasing the mouse, but in the second sentence, the mouse is chasing the cat. So that is why the order is important. And we will cover this part when we will study what positional encoding is in the next video. We will be covering this topic in the next video, so don't forget to subscribe and press the bell icon so that whenever I upload the video next time, you are notified and you can watch this video as early as possible. We will be covering positional encoding soon and we will see how adding order or taking order into consideration is important. But for now, let's focus on this part, and that is what are task specific contextual embeddings. And I have a very nice example for it that this will make which will make everything clear. So when we find out the contextual embeddings, then the vector representation of that word tries to provide every information about that word. For example, how is it used in the sentence, what its meaning is, what are the words that are influencing it, was it its syntax, what kind of tone that word carries. So it's more like a general embedding that carries everything that it can capture about that word. But in real world applications, what we want is something that is more task specific, because that is when our accuracy improves, that is when our model is most appropriate to use, right? For example, let's say I'm doing sentiment analysis, and let's say I have a sentence and I am deciding that whether it's of positive sentiment, negative sentiment, or whether it's neutral. Now, for this specific task, if I use this general contextual embeddings, then reaching to a conclusion from a general contextual embedding would take a lot of time for the model. The accuracy might not be that great, and this is a problem. What we want is that somehow, if our contextual embedding can speak out that this is the sentiment of this word, then that would have been that would have been far better, right? Because this is covering every aspect of the word. But let's say we want only sentiment part, and we want that our embedding should only highlight that. We don't care about other aspects. We don't care about its meaning as. The only thing that we care about is what is the sentiment of the word, so that for every word, now that I know the sentiment, I can finally give the conclusion that this is the sentiment of my sentence. So this is what task specific contextual embedding is. I have a very nice analogy to give the to explain this. So you can consider contextual embeddings like a Swiss Army knife that has so many functionalities, right? It has a knife, it has a opener, it has everything. And if you look at the image of it on internet, you will really appreciate that how carefully it has been crafted. But if I am cutting a tree, then there's a high chance that I will use a tool that is more intended to cut a tree. And I will not use my Swiss Army knife, right? I will use an axe or I will use a saw to cut that tree. So for specific tasks, we use task specific tools. We don't use something which is very general, something which is very common until we have an emergency, right? So, so that is what the difference. That is what the difference is between our contextual embedding and task specific contextual embeddings. Contextual embeddings are like a raw picture where everything is there in the picture, but nothing has been emphasized yet. And task specific contextual embeddings are when we emphasize a particular part of the picture for a specific need. Okay. And I have one more example to give you. For example, let's say I have a sentence where I say Apple released a new product. Apple released a new product. Then in this sentence, if I consider Apple, then the contextual embedding will be same, right? But if I will consider task specific contextual embedding, then what will happen? That let's say if I am doing sentiment analysis, then the embedding that I will get from here, that will speak out that the sentiment of this word is neutral. Similarly, let's say if I am doing named entity recognition, then the embedding of Apple should speak out that this is organization. So we want task specific word embeddings, task specific contextual embeddings that out speak out that this is what it means based on the task that we have at hand. Okay, now how do we reach from contextual embeddings to task specific contextual embeddings? Because these task specific contextual embeddings are way better. We can converge to our final output faster, the training is faster, accuracy is higher, because our task that we have, the embeddings that we are getting, they are more aligned with the task. So that is why we reach to the solution, we reach to the end output faster, and accuracy is also higher. Now, how do we reach from contextual embeddings to task specific embeddings? The simplest way is to train our to use our data that we have. So if we are working on sentiment analysis, then the data that we will have, that will be also related to sentiment analysis, where we will have a sentence and we will have the corresponding sentiment. So using this data, we can convert our contextual embeddings to task specific contextual embeddings. And how we can introduce this? How we can introduce our data so that our embeddings can learn from the data that we have? How we can introduce that? If I just go up, then this is where we left, right? Where when we were finding out the contextual embedding. Now, clearly in the SoftMax part, we can't do anything. The only thing that we can do something is this dot product part where we are finding out the weights. So now let me come down where I have rewritten this equation. So this is the sentence that we are using, use Apple phone, and this is the new contextual embedding of the word Apple. So if you see here, then if I pick up any word, let's say since we are finding out the contextual embedding of Apple, let's consider Apple here. Then the word embedding of Apple is used in three different ways. The first one is here, the second one is here, and the third one is here. And if you look at these three word embeddings, you will understand that they are used differently. They are solving different purpose. Here, the word embedding of Apple is asking the word embedding of use that how much similar we are, how much aligned we are. And this query is being asked to this word embedding, right? And this is the associated value, the actual value of the word embedding of that word, right? So every word embedding of the word is used in three different ways, and we call them as query, key, and value. Query is this part which is asking that how much similar we are, and to the embedding to which it is asking, that is what we call the key, and the actual value is called the value, okay, which contains the actual information. Now, since a word embedding is used in three different ways, why do we use the same embedding for three different purposes? This is not the right way, right? If I am good at cooking or if I am good at teaching, that doesn't mean that I have to do everything. I might I might be knowing little bit of cooking, I might be knowing little bit of teaching, but that doesn't mean that you let me cook food as well and let me teach students as well. It's good that for every purpose we have a dedicated embedding. So if I am cooking food, then there should be a dedicated person who is acting as a teacher. Or if I am teaching, then there should be a chef, right? So specific task specific things are always better than general things. Here, the same word embedding is used everywhere, but that is used in three different ways. So it would be better if every embedding is used differently. By that I mean different embeddings are used, right? Now, how do I introduce this three different embeddings based on this single word embedding? So before explaining that, I want to touch more upon what this query key value embeddings are. So if you see here that if I consider a particular sentence, let's say the movie was not bad. The movie was not bad. If you see here that with bad, you have note here. If I am finding out the task specific contextual embedding of bad, then what will be my query? My query will be that look for sentiment modifier around me. Sentiment modifier. Is there any word, is there anything in the context that can somehow change my meaning? So this is the query that this embedding will ask. It will highlight that up. Okay, this is the question that it has in mind. Now we have embeddings of every word. Let's say movie, was, not, and bad. So what this is telling that what it has to offer. For example, the key embedding of movie will say that I am a noun. Okay. Was key embedding of was will say I am a verb. Key embedding of not will say that I am a negation word. Now this is something important for us, right? And key embedding of bad will simply say that I am a negative word, or let's say I am a negative, I am used negatively, right? So this key vector represents what it has to offer, what is relevant for your query, what it has to offer. So I have a very good analogy for it. For example, let's say you are in a party where there is a crowd of people. Now, if you want to learn Python, this is your query. You're looking for someone who can teach you Python, right? Now, from that crowd, there are people who are designers, there are people who are Python developers, there are people who are software engineers. So, these labels, the designer, Python developer, software engineer, these labels are the keys. Depending on these keys, you are deciding that who can teach me Python, who can teach me Python, right? So the key reflects what it has to offer. So someone who is Python developer, you can think that he is someone who can teach me Python. But if someone is a software engineer, you can decide based on that label that how well he will be in order to explain me Python. So based on these keys, you decide that first of all you define that what you want, what you are looking for. Then these keys reflect that what they have to offer. And this value is the actual information that they have. For example, if I reach out to a software engineer, then they might know 50% of Python, or if I reach to a designer, they may say that I just know 5% of Python. So, what information that I am looking for do they actually have? This is the actual information. Okay, they might know 95%. If I'm looking for, if I reach out to a designer, then they might know 5% of Python, but 95% of designing, right? So this is the value that they actually have to offer. And if I just do the dot product of our query vector and our key vector, this tells that how much aligned our vectors are. So if I'm looking for a Python developer, and if I'm looking for someone who can teach me Python and if I find a Python developer, then this score will be high. This attention score will be high. And that reflects that I need to pay attention to this pair. This carries more importance. And when I take its dot product with the value, what does that represent? That represents that how much information I actually got. Okay, so let's say uh, from the Python developer, let's say I get this value. Then what is the value that this Python developer can actually offer? It will be 90% of that value, right? Because they were 90% alike. So that is why the value that it can offer will be the 90% of the value that it carries. So this is the intuitive meaning of these three vectors. Now you see here that instead of three different vectors, if I considered the same vector, then it would have been very difficult for a single vector to carry three different meanings or three different objectives, right? Because original embedding cannot perform each role without conflict. If I want to query something, then I can't be answer for that, right? That is very conflicting. So that is why we need three different vectors, and that is why we thought that why not we break our original word embedding into three different vectors, because ultimately what we are doing, that we are doing three different tasks with our same embedding, which is not good, right? So that is why we have three different embeddings that perform their individual tasks, and ultimately we get the result. So what I'm saying, that this, how we can write this new contextual embedding now? We can write it like query vector of apple into key vector of use, then value vector of use. Similarly, we will have query vector of apple, we will have key vector of apple, then value vector of apple, and the last one will be query vector of apple, key value of phone, and here also the value of phone. So now instead of this, we have this. Now we have three different vectors for each of the task. For each task, we have one different vector. Okay, because you see here that every embedding is doing three different tasks, so that is why we need three different embeddings, and we land up with something called query vector, key vector, and value vector. And we also understood that what each vector represents. The query vector tells you that what is it looking for. Key vector tells you that what it can offer, whether it's relevant or not. Value vector tells you that what info it has and what it can actually give you. So this is how the entire uh, thing is. And if I just I think I didn't give the value example for this particular example where we were looking for the query, we were looking for the task specific contextual embedding for bad. So query was look for sentiment modifier. Then we reached to the conclusion that the key vector of not is something that is important because it tells you that I am a negation word. Now what we note of it will look like that how negation changes sentiment. How negation changes sentiment. So what will happen, that when we will find out its contextual embedding, then its contextual embedding, originally if we consider its contextual embedding, then that would be, I mean if we just consider its word embedding, then it would be negative, right? It would be strongly negative. But when we consider its task specific contextual embedding. Then it shifted to soft softened negativity. So it will be very close to good. The new task specific contextual embedding of bad will be very close to good, because now it's also depending on the context that is around it. And since we are doing sentiment analysis, so this is also task specific. So I think everything up till here is clear. If there are any doubts, do let me know in the comment section and I will clear them out. Now, how do we find out the query vector, key vector, and value vector from our embeddings that we have, our word embeddings that we have? So this is one vector, and from this vector, we want to find out three different vectors. There are not many ways actually in order to convert one vector into another vector. One way is scaling, but that will not help us much. And the another thing, the another method through which we can convert our word embeddings into query key value embeddings, that is through linear transformation. Now, what is linear transformation? Linear transformation is a mathematical way through which you take in the input, which is a vector. Some processing happens here, some linear transformation happens here, and the output that you get from here is the transformed vector or the new vector. Okay, and how do we do it? We take a matrix and we multiply our vector with it. It's that simple. Okay, because this matrix is what the it is what helps us in it is what that helps us in linear transformation. Okay, so how does matrix helps us in linear transformation? So let's say I have this original vector, which is my word embedding of, let's say, apple. Then I have a matrix. Let's say I call this matrix WQ. Okay, I call this matrix WQ. If I multiply my matrix with this vector, okay, so this is 2 cross 2, let's say, and this is 2 cross 1, let's say. I'm sorry, actually, I should write it here because there is 2 rows and 1 column. Now we were doing it right. We will write it here. There is 2 rows and 1 column. So by matrix multiplication, what we will get? We will get a vector which is also of same dimensions, right? So we take this matrix and we take our original vector, we multiply with it, and we get our new vector which we call the query vector. Similarly, we have another matrix which we call WV, and we get the value matrix out of it. Then we have another matrix called WK. We multiply our original word embedding with it, and we get the key vector out of it. So from one embedding, when we apply linear transformation, it get transformed. It gives us another vector, which is query key value vector. Okay. So in short, linear transformation is nothing but a mathematical operation through which whenever you give it a input which is a vector, then in output you get a new vector, that is the transformed vector. Okay, and how you are doing it, how do you apply linear transformation on vectors? You multiply the vectors with a matrix. That matrix carries the transformation logic. Okay, and how do we find this matrix? Now this is the question, how do we find these matrices? So matrices are nothing but it contains numbers. How do we find these numbers? These numbers are nothing but weights and we can learn them through the data that we have. So finally, from our dot product, we reached to the point from where we have something that can learn from the data that we have. And this learning will happen through backpropagation. And now we are clear with what we want. We want task specific contextual embeddings from our word embeddings. And how we are doing it? We are doing it through this equation that we have here. Let me highlight this part. We are doing it through this equation where we have decomposed our original vector into three vectors which we call query key value vectors. And how are they obtained? They are obtained through linear transformation. And how we are doing that linear transformation? We are taking up a matrix and we are multiplying that vector with it in order to get the transformed vector. And how are we getting this matrix? This matrix is consist of elements, and these elements are nothing but weights, and we learn them through the data that we have. And how the learning happens? Just like how the learning happens in neural networks through backpropagation. So now our embeddings are dependent on our data. It's learning from our data. So this is what finally self attention is. It takes in the word embedding and it gives you task specific word embedding. And these embeddings are so good that they are used in state of the art models. For example, transformers, they are used in transformers, and you can use these embeddings for your own purpose as well, as long as you have a lot of data to train your model, to train this model, or in order to get these weights and biases. I mean the weights here. Okay, so these embeddings are then used in our transformers. When we will be covering transformers, then these task specific contextual embeddings will be used. So this was the video about self attention. I know I have spoken up a lot, and very it took a lot of hard work to make this video because I had to refer multiple sources for it. If you like this content, please give it a thumbs up and please subscribe to my channel. A lot of hard work has been put into this. Now, so this is what self attention is, right? Now, one point that I have to add here is that these matrices are used for every other embedding. For example, let's say I have another word instead of apple, let's say I have used, and I am finding out its query value key vector, then this same embedding q will be used. Okay, because we are extracting the same aspect. We are doing sentiment analysis, then we want to find out the sentiment of every word. So that is why these weights, these matrices will remain same. Now, in attention is all you need research paper that is around transformers. How do they define it? They define it this way: softmax of our query vector and key vector, and then we are doing its dot product with value vector. Because if I just go up, then here also we were applying softmax, right? So that is why here also we must apply softmax, because ultimately these are dot products and we need to normalize them. So that is why we apply softmax on it and then we multiply it with the value vectors. So this is what your task specific contextual embeddings are. But in research paper, we have an additional term, and that is they have divided this with dk. Now, why have they divided it by dk, and what does this dk is, square root of dk is? This dk is nothing but dimensionality of key vector, and this query vector, key vector, value vector, they all are of same dimensions. So instead of dk you can have dv or dq. That is not the concern. The thing is that we are dividing it by the square root of dimension. And why we are doing it? Now we will see it. That why exactly do we divide it by a particular term? Let's just first understand the nature of dot product. Okay, so we are considering two vectors here, and we have a dot product of these two vectors. Now, there is one property of dot product, that if the dimension of these vectors increases, then the variance also increases. This means that if I find out the variance of vector q and k, dot product of q and k, then what will be that? That will be something like variance of this, right? Which is nothing but, now here we make one assumption, that is these vectors q and k, they have mean 0. And why do we keep mean 0? Because we don't want to introduce any bias. That is why the mean is 0. And the variance is approximately 1. It's 1, equal to 1. Okay, why 1? Because that depends on the initialization technique. The matrices that we consider, WQ, WV, WK, the weights with which we initialized, those weights had variance 1. Okay, because this is how we do initialization. There are certain initialization techniques. So here we make the assumption that the variance is 1. So every element that you will see here, that will lie in the range of -1 to 1, and they will be centered around mean. Okay, so this is what these assumptions mean. And this is necessary for table training. That is why we keep such kind of conditions. Now, what will be the variance in this case? These two vectors are independent because their matrices are independent. How we can write it? We can write it variance of this, and since variance of individual term is 1 and these vectors are independent, so that is why it will be roughly 1. And since we are summing it over n terms, so what will be the variance? Variance will be approximately n, right? So if I increase the dimensions here, for example, let's say initially you had 4 elements, so this n will be 4, right? Because since there are 4 terms, so every term will be multiplied with every corresponding term of k vector, and we are just summing them. So this n will be 4. So if I take 100, then the variance will be 100. So clearly, when we are increasing the dimension of these vectors, the variance is also increasing. Now you will say that what's the problem with increasing variance? The problem is that because of these bigger numbers, because of this variance, what will happen, that the values that we will get from here, the values that we will get from this dot product will be from a varied range, right? So what exactly variance is? Variance is the spread of values. If you have a high variance, that means your values are scattered. So this high variance due to high dimensionality represents that the values that we will get from here, they will be more scattered, right? And since these values are scattered, what will happen that if I will find out that what will be my loss with respect to this, let's say I call it Zi, with respect to this Zi, then that will be softmax 1 minus softmax. Why? Because the problem is not high variance. The problem is the softmax that we are applying. So if the variance is high, that means the values will be more scattered, the values will be more varied, because of which when we will apply softmax on those values, then what will happen that the values will vary a lot. Some values will be close to 1, some values will be close to 0, which is not good, because if we will find out the derivative of loss with respect to this term, then it will be softmax 1 minus softmax, because the derivative of softmax is actually softmax 1 minus softmax. Softmax function we know, right? It's nothing but zi summation of I equals to 1 to n. So this is what softmax is for ith term. So what we are saying that if the values are varying a lot, so if there is a value that is close to 0 or some value that is close to 1, then this loss function will be 0. This derivative will be 0. Now this is vanishing gradient problem. This is vanishing gradient problem, right? Because of which our model will stop learning, which is a big problem. If our model will stop learning, then the parameters will not update and entire training process will completely stop. We will never be able to reach to the actual values of our weights, right? So that is why in order to balance this variance due to increasing dimensionality, we divide it by square root of dk, because we know the property of variance, right? If y is equal to cx, then variance of y will be equal to c square variance of x. So whenever a constant term comes out of the variance, then square happens. So if we are saying that the variance is n times, so in order to balance this out, what we will do that we will divide it by dk. So when we will take its variance, then this dk will come out as dk, which is nothing but the dimensionality, which is nothing but the n. And since variance is 1, n, we will always get the final variance as 1. So that is why we divided by the divided by the square root of dimensionality of key vector or query vector or value vector. I'm just summarizing again. If you find it a little bit confusing, let me change the pen color. So what I'm saying that in order to understand that why do we divide it by dimensionality of k vector, we need to understand the nature of dot product. And that is that whenever the dimensionality the of the vectors increases, then the variance of the dot product also increases. And we saw the entire mathematical derivation here, right? How the dimensions were increasing based on our assumptions. And these assumptions are based on the initialization techniques that we used. So since the variance is increasing, the problem is not the the problem is not with the dot product. The problem is that because this variance is increasing, we will get more scattered values. So if some values, let's say 0.4, some values, let's say 10, then what will happen then when we will apply softmax on these values, then the value that is bigger, that will be more close to 1, and if value will be smaller, then that value will be more close to 0. So it is the nature of softmax that it is more attracted towards the bigger value. It assigns more value to it. And if the difference between the values is large, then what will happen that because of this big difference, softmax will favor this more and this will have a higher value. And if it's close to 1, then our gradient will be close to 0. And ultimately, since our gradients are close to 0, vanishing gradient problem will happen. Our weights will stop learning, our weights will stop updating, and ultimately the training process will stop. So that is why high variance is a problem, and that is why in order to balance out the variance so that it's always close to 1, we divide it by the dimensionality, the square root of dimensionality of vector k. I hope everything is clear. If you still have doubts, do let me know in the comment section and I will help you out in the best possible manner. And now let's understand that what are the similarities between self-attention and Luong's attention or Bandhanav's attention. If you haven't watched the video on attention mechanism, then I would highly recommend to please go and check out that video. I have explained everything in detail. So self-attention is also a type of attention mechanism. But why do we call it self-attention? Because in Luang's attention, Bandhanav's attention, or the entire attention mechanism that we read, we always had two sequences of sentences, right? One was that was going in the encoder, and the other one was that was coming out from the decoder. We always had two sequences. But in self-attention, we have a single sequence of words. We have a single sequence. So that is why it's called self-attention. Now, why do we say that this is attention? Because we have similarities here. The query vector of our self-attention is similar to SI vector of Luong's attention. The key vector of our self-attention is similar to our hidden state of jth vector, and similarly value vector is also similar to hj. If you don't understand this, how am I mapping these query key value vectors to this SI, and HJ, I would highly recommend to please go and watch the video on attention mechanism where I have explained Luong's attention. You can jump to that time step and you will see that they are actually very similar, because ultimately what we do there, that we take our SI, we take our HJ, we take their dot product, then we pass it through the softmax layer, and then we are using it with HJ in order to find out the final value. So same way here we have query key value vector. So this is also attention, this is also attention. Here we have two sequences involved, and here we have a single sequence involved. And since we have a single sequence involved and we are focusing only on that sequence, that is why it is called self attention. Okay, now let's understand that what is the problem with self attention. Everything looks good, but there is a big problem, and that problem is that our query key value vectors, the mechanism that we discussed so far, that is only able to capture a single aspect. For example, when we were considering that query where we were asking that look for sentiment modifier, then that is the only aspect that I am capturing. I know that is related to sentiment analysis, but that is the only aspect that I am capturing. What if I want to find out that, okay, this is the sentiment modifier which I was looking for earlier, but what if I want to look for specifically sentiment amplifier? For example, let's say if something is negative, then it is making it too negative. If something is positive, then it is making it too positive. For example, very. Very is a specific word that emphasizes whatever you are saying. For example, very good. Good, but extra good. Right? So What if I want to capture that aspect of sentiment as well? But when we define our query key value vector, then we are just capturing a single aspect of it. What if we want to capture multiple aspects? Then that is where our self attention model fails. I have a very nice example to give you. For example, let's say I have a sentence that the woman saw the man with the sheep. The woman saw the man with the sheep. Now, in this sentence, if you look, I will take a moment. I think this sentence is not right for it. Let me find another one. So instead of sheep, let's consider glass here. I think that this is a better example to consider. So what this sentence means that the woman saw the man with the glass. Now there are two meanings that are there in this sentence. The first one is that this woman saw the man through a glass. Okay, and another meaning can be that this woman saw the man with the glass. Means these two things together. The man was carrying that glass and the woman saw him. So these are the two meanings that this sentence carries. Now, with a single self attention head or single self attention mechanism, it would be very difficult to finally understand that what this sentence means because it carries double meaning. We need a more discrete, more refined way through which we can finally remove the ambiguity in this sentence and jump to a final conclusion. So, a single self attention model will never be able to achieve this task. It would be better if we have multiple self attention heads. For example, the first self attention head where we are focusing on subject. We are looking for what our subject is. For example, here it's woman. It should be A or woman, right? And let's say we have second self attention head, a second self attention model where we are focusing on object plus modifier. Okay, so it will be man plus with a glass, right? So if our self attention model, if we are using multiple heads, then one head will focus on the subject, another head will focus on object plus modifier, and then we will finally understand okay, so the sentence is actually that the woman saw the man with the glass, means the man was carrying the glass and the woman saw him. This is the right way. This is the more unambiguous way, right? Because through this way, when we are using multiple heads, then we have reduced the ambiguity. We are now more focused, more clear. We are capturing the multiple aspects of the sentence. Because when we have a single self attention model, then that carries only one relation. But in a sentence, we don't have just one relation. There can be multiple relations, and we need to capture every aspect. And to capture every aspect, we need multiple self attention models. This is where multi head, multi head attention comes. It is self attention, but instead of single self attention model, now you have multiple self attention models. And how it looks? It looks this way that this is your multi head attention where you have multiple self attention models. You provide input, and that input is your word embedding. Let's say monkey, then that word embedding will go to into every self attention model because different aspects or different relationships will be captured. Then you will have another word again that will go as input, and what you will get as output from this self attention, you will get the um, contextual task specific contextual embedding of monkey and 8, but that is just one. You have two more heads, so you will get embedding 4 from there as well. Okay, so this is how it looks. And what we do that once we have got these embeddings, what we do that we concatenate them. How do we concatenate? For example, this is my y1 monkey. Then I have my y1 bank. I'm concatenating them. You know what concatenation is, right? When you put two vectors adjacent to each other and you make them a single vector. So you are concatenating all the vectors that you have here, and once this concatenation is done, because the dimensions have increased, we want the original dimensions again. That is why we pass it through a matrix, or we multiply it with a matrix, which is nothing but we are just transforming this vector back into the original dimension. And how do we do the uh, transformation from one vector to another vector? Through linear transformation, and for linear transformation we use a matrix, and the weights of these metrics will also be learned through backpropagation, through our data. It will be learned from the data that we have. Okay, so this is what we do in my multi-head attention. And this ensures, because random initialization of weights happen, plus they are independent, so this ensures that matrices are not identical and they are specialized differently. Okay, so if the weight matrix, the query key value matrix that I will be considering here, then the associated matrices with these vectors w cube, wk, wv, these independent matrices will be initialized differently here. So the query matrix that we will have here and the query matrix that we will have here or here, these three matrices will be initialized differently. That is why their values will be different, and that is why they will end up differently. That is why the vectors that you are getting out, they will be different. And then we will concatenate them. Their dimensions will change, but we want them to be in the original dimension. That is why we will apply linear transformation on them. And linear transformation also has one more intuition associated with it, because through linear transformation, since the weights are associated with it, so it kind of tells you that how much importance each aspect has. It's not like all the relations that you have captured are equally important. There might be certain relations, there might be certain aspects of the sentence that are more important. So in a way you are assigning weights to them. In a way you are capturing that which aspect carries more information. That is why you apply linear transformation. So I hope multi-head attention is clear, and the example that I gave you was clear enough, because the example that we considered earlier, where we were finding out, where we had a sentence that movie was not bad. In that sentence, the query vector that we considered, that look for sentence modifier, that was something that was capturing only one type of relation, right? We want that multiple aspects must be covered. For example, I gave you the example of very, where our query vector can be that do we have any emphasizer, any word that emphasizes more. So we need to capture multiple aspects in order to jump to the conclusion faster. That is why we felt the need that we must have something like multi-head attention, where instead of single attention, self attention, we have multiple self attention heads, and each one capturing different aspects of the word in a particular sentence. So I hope this long video, I know I have spoken a lot and this video has been very long, but I will add timestamps to it so that it's easier for you to jump to a particular section. And I think the examples that I gave, the analogies that I gave, the explanations that I gave have cleared all your doubts, and now you clearly understand what self attention is, every detail of it, how we started from vector embeddings and how we reached to task specific contextual embeddings. Everything is clear. We also understood that why in the all you need is attention, a research paper. In that paper, why the equation that we saw was divided by the dimensionality of k vector, square root of that dimensionality of k vector. We also understood that, and we covered that how self attention is similar to Luong's attention, and how self attention is problematic, in which situation it is problematic, and how multi head attention comes into the picture to solve its problem. And this multi head attention is then used in transformers model, which we'll be covering very soon. I have put a lot of hard work in this video, so please give this a thumbs up, show your love in comment section, and subscribe to my channel. Now in the next video, we will cover what positional encoding is, where we will be seeing that how order is also important, and how we must introduce the order in which the word is there in the sentence, in which order the words are there in the sentence. That information is also important, and in our task specific contextual embeddings, we must incorporate this information. Everything around positional encoding will be covered in the next video, so stay tuned. Thank you so much.